encourage you, like, while we're doing this talk, I like, for one purpose of writing up these rules here is so that I don't have to write them down and waste time. But I'd encourage you to use your personal boards as I sort of explain what a proof using this rule is, to just try and prove some things, and I'll come up with some examples at the end. So basically, what we're talking about today is we have a logical language. We also introduced a semantics for first order logic, which on the Discord you can see the notes from last week if you want to review that or have that as a reference. But here we are introducing a proof system for first order logic, and the choice here I'm making today is to use natural deduction. And a key point about proof systems is that they are syntactic entities, and the means of inference should be isolated to just recognizing pieces of syntax and the structure of a formula, rather than
Find the notes.
I think they're in the general channel, by the way.
I'm looking at that post and I don't see it.
Wait,
Yeah.
what? Let me have a look.
I can see it in the general channel of the Discord.
Oh my god, I'm blind. I was looking at Daniel Murphy's post. Okay, thank you.
Oh, right. No, I posted them.
Yeah, okay. So I want to start with an example proof, because just like going through the definition and all the different details of it won't probably conjure the right images in your mind. But I'm going to use an argument that Gensen presented in his paper, in which he introduced the natural deduction system. And what distinguishes the natural deduction system from other logical systems is the strategy of proving some conclusion from some collection of hypotheses. This stands in contrast to like Hilbert style deduction systems, in which you essentially write down axioms which inside them embed the relations between logical connectives, whereas the sort of point of the natural deduction system is to explain how we can introduce and eliminate formulas with logical connectives. So the example argument he gives is explaining how we would, as logicians, argue that this is a valid formula. I'm on the first board, by the way. And so the idea is, so we want to show that x or y and z implies x or y and x or z. So he says the argument runs as follows. Suppose that either x or y and z holds. So key words here are the supposition. So this idea of supposition, which I'd like to think of as introducing some hypothesis into context, is made absolutely explicit in natural deduction. And the second is sort of recognizing that to have a statement which has the structure of this or this, it suffices to argue by cases on which one you have. So the argument continues. We distinguish the two cases: one where x holds, and number two where y and z holds. In the first case, it follows that x or y holds. So the first case is where x holds, and also x or z. Hence, x or y and x or z also holds. In the second case, y and z holds, which means that both y and z hold. From y follows x or y, and from z follows x or z. Thus, x or y and x or z again holds. The latter formula has thus been derived in general from x or y and z, and from that you infer the implication. So you'll notice that he just sort of says, like in the first case, it follows that x or y holds. He doesn't sort of explain why x or y follows from x. But this is sort of a basic inference that he's claiming should just be a feature of the proof system and not something one needs to justify while performing the proof. So I just spoke out loud what how he presented that argument, and how we would, and the way we would present this argument is sort of linearly, because that's the way we write things down. But in natural deduction, it's sort of it's shown in a structural manner. So I'm going to start with it's sort of split into two arguments, and the first one was where x holds. And so I'm going to start with x, and the idea is to every time you sort of make a deduction, then you have a premise above the line and the conclusion that follows below. And so from x, I'm going to draw a line and just write x or y below. This becomes justified as a usage of a particular rule, and this one is called or introduction number one. There's two of those rules. And we also said that from x, what was it? X or z holds. And that's or introduction one again. And then there was a line about we've deduced both of these facts, that x or y holds and x or z holds. And in our system, this is sufficient for the claim that x or z holds. And this is the and introduction rule. So that was one case, and this stands as a proof of the statement at the bottom from the collection of assumptions used at the leaves of this tree structure. So so now I want to argue the second case, that I can go from y and z to the same formula at the bottom. So I'll do that now. So we start with y and z. I want to deduce x or y first. So let me. We claim that we can extract from this the fact that y is true, and this is and elimination one. And in parallel, also do the other one. Y and z also gives us z. I haven't given myself space to write the rule at the end, but that's okay. Oh, actually, I need another line below this.
But you might want to mention, Billy, that that's and elimination 2, right?
No, that's and elimination 1. Are you talking about the first one, or as in the
second
y
one.
and z? Yeah, the second one is and elimination 2. Yeah.
Yeah, so it's the first time we've used the second rule. So you didn't write it, but maybe it's worth mentioning.
Yeah, I just didn't have room. Okay, so oops. We have X or Y here and X or Z here, and both of these are all introduction 2. And the AND introduction rule then gives us X or Y and X or Z. And this doesn't quite line up beautifully, but let me just actually, and this line needs to be even longer. So the way we then put these together, we're arguing that it's reasonable to that these arguments suffice to get us from the assumption of X or Y and Z to the conclusion that we've now proved twice. And the way we picture that is by giving that as an elimination of the formula X or Y and Z. And let me put a rule under this. And from the fact that we have X or Y and Z, and we have a proof of this conclusion X or Y and X or Z from either case, we can make that conclusion below the line. Yeah. But I'm not finished yet. I'm going to write or elimination here. As written, this sort of appears to depict the fact that from the assumptions of X or Y and Z and X and Y and Z, you can deduce the conclusion X or Y and X or Z, because these 3 formulas all appear as the leaves of this tree. These are all we're within the context in which these things are being assumed. But a part of the OR elimination rule is that after this last line, we can discharge our assumption of X in the first proof, and I'm gonna mark these dischargings with a natural number, and of Y and Z. And I would also write 1, 2 next to the OR elimination step. And so now so within those 2 smaller subproofs, these the X's in the first proof are not discharged, and the Y and Z's in the second proof are not discharged. But once you pass through this this bottom line, they are no longer assumptions. We are claiming that we do not need to assume that X is true or that Y and Z is true to get from X or Y and Z to X or Y and X or Z. And so finally, it would maybe appear that
I didn't follow that last comment. What do you mean by we're no longer making these hypotheses? I mean, this overall construct on the board is, I could write that as x1 ... y or z ... and then this conclusion at the bottom, right? They're still hypotheses.
They are hypotheses to like if you picture the argument I was making where or that Gensen is making, that let's consider case 1 where X holds. So within that environment where you're considering X to hold, within that case, X has been assumed. But the point of the or elimination rule is that once we've entered those two cases separately, the assumptions of x and the assumption of y and z are assumptions within those cases. But in my deduction to deduce x or y and x or z from my assumption of x or y and z, I don't need to make any assumptions of x or of y and z.
So you have two forms of discharging hypotheses in this system: the implication, introduction, and and this one. Mm-hmm.
Yeah, exactly. So in this proof, I've proven x or y and x or z with a collection of assumptions, which from the singleton collection of assumptions, which is just x or y and z. But if I want this to be a standalone proof of the formula at the top of the board that doesn't rely on any assumptions, at this point I then can discharge the usage of this assumption to gain the final formula, which I'll write it out. And keep writing y instead of or.
Wait, I'm really confused about the terminology. Like, it sort of makes sense, but I'm kind of confused about the appendages of like the or I1 or the and I that are positioned next to each line.
Yeah, so those are these are all different instances of a rule, which I'll go and explain in full generality soon. Some of them have indexes which sort of attach to particular discharged assumptions. So the superscript in the last deduction of implication introduction with the superscript of 3, that is saying that at this point in the proof, I discharged my assumption of x or y and z. So previously my conclusion was x or y and x or z. That's no longer my conclusion. My conclusion is now x or y and z implies x or y and x or z. And I have discharged because the antecedent of that conditional is x or y and z. I am able to remove my assumption of x or y and z from the leaves of my proof.
Mm-hmm.
And a similar thing happens with the or elimination, where I'm eliminating like the assumption of x and the assumption of y and z in those two subproofs are still like present as assumptions in those two subproofs, but in the global proof they have been removed by that. Those assumptions have essentially been justified by the usage of or elimination on the formula x or y and z. Does that make sense?
I am still really confused, but now I'm just getting. I'm getting.
Can I give it a shot? So the labels are merely labels of which instance of rule that you've used. At the end of the day, that's all that they are. And all the different rules are what's written on these tombstones, right?
Yeah, that's what I gathered so far. I see.
Yeah. Now, some of the rules are more and less complicated than others. Some of them are very simple, like the and introduction is simple, or introduction is simple. But then some of them involve going into your proof and reading the structure and then doing this thing that Billy is talking about, which is discharging hypotheses. But it just means that some of the rules are more complicated than others. But the labels, like as per your question, all they are labels to the reader as to which inference rule that you're using. Does that make sense?
Wow. Yeah. There's a lot of rules.
Yeah, there's a lot of rules.
So for example, like the and introduction rule, like looking at this tablet over here, it has A and B above the line and A and B below the line, and it's labeled with this and introduction rule. For this particular rule, you can we could just have not written the label, and there's only one rule that looks like this, so you could sort of identify it. But say if I was deducing A from A and A in the sort of in the and elimination rules, I wouldn't know whether that's a usage of the first elimination rule or the second. So I don't know whether or not that's important to you is up for debate, but they just sort of they can provide clarity into what rule is justifying this inference. There can be sort of overlaps in other usages of rules.
Maybe I might make a comment on the role of hypotheses. So, in my opinion, natural deduction is kind of a strange system because of the role of the hypotheses, which are hidden structure in the tree. So keep in mind that, so if you look at these three branches that Billy has above this line that has the or elimination rule with superscripts 1, 2. In these three branches, this kind of flowing into the deduction rule, those branches have hidden information, which is the active hypotheses. So in the leftmost branch, there's a single hypothesis that's active, labeled 3. In the middle branch, there's a single hypothesis, which is active, labeled 1. It just occurs twice. So this is a hidden form of what we would call contraction in sequent calculus. And in the third branch, there's a hidden hypothesis of y and z. And in that deduction rule, you get to name some hypotheses that are used in the deduction rule. And you can see those in the abstract kind of prototype of the rule on the stones. But those, the reason I say hidden is if you look at the final line of the middle branch, x or y and x or z, you don't see that hypothesis written there. You have to read all the way up to the leaves to know what hypotheses are kind of flowing to that point in the proof. But when you read a natural deduction proof, you should have in mind that these hypotheses flow from the leaves downwards, and then you need to know what's available every time you make one of these elimination deductions. So that hidden structure I find kind of the most confusing aspect of natural deduction.
Yeah, it's weird. I get it so far. It's nice how this can be formalized. I guess the point of this is to be natural or something. I don't know.
Yeah, I think there's meditation involved in the construction of these rules and arguments as to why this is what a proof system is. But you can debate it. Genson's paper introduces two main proof systems. There's natural deduction and there's sequent calculus, and they're both different philosophically. I can hear a roaring bell. That's right. Do you want to add further comments, Billy?
Well, in Genson's paper, he does say essential aim, it has a close affinity, or he claims it has a close affinity to actual reasoning, which had been our fundamental aim in setting up the calculus. And also he also claims the calculus lends itself in particular to the formalization of mathematical proofs. So yeah, it can be sort of I found in if you're in a formalized theorem prover or something, it's useful to have you have the computer to just tell you what hypotheses are available. So then I guess you don't need to be too bothered by the need to keep track of what hypotheses are available in which context. Anyway, let's continue on then. Give me a second. I might as well formally define what these figures are, and in full generality, or as much as I can. So first of all, I'm on the second board now. So Genson calls these inference figures. So an inference figure, or sometimes I might just say inference, consists of one or more formulas which are called the premises of the figure. He actually calls them upper formulas and the others lower formulas, but I'm just interchanging my own terminology here. There is also a single formula called the conclusion. Of the figure. And so we write an inference figure with premises A1 up to AN. I'm just remembering something. I should actually say 0 or more premises. So we write an inference figure with premises A1 up to AN and conclusion B as you simply you list all of the premises above the line, and below the line you write the conclusion. So this is the structure of an inference figure, and it may as well be identified with the symbols you write on the page, like this, and also what constitutes a what a proof figure is can be sort of formalized as a particular kind of graph, which has some sort of there's some strengths to doing it that way, but I'm not going to do it that way. Instead, I'm just going to sort of describe to you how to assemble a bunch of inference figures into a valid proof figure. Before I get to that, another definition is of a deduction rule. So a deduction rule is an inference figure schema. Which makes use of formula variables in place of subformulas of the premises and conclusion. And so what I mean by that is exactly what these are deduction rules, what I've written on these tablets here. So they A and B here are not themselves, like, they're not a particular predicate or a propositional variable or a particular formula. They're schemas for telling you how to take any if you take any formulas like if you pick two formulas and replace all the instances of A with the first formula and all the instances with B with the second formula, then you obtain a valid inference figure. So I'll just say that here. A valid inference figure is obtained by substituting formulas for the formula variables. I won't write this, but some deduction rules possess side effects of their usage. For example, some rules can cause some assumptions to be discharged, and some other rules also have conditions on their usage, which becomes relevant when we use these quantificational deduction rules over here, which also refer to the undischarged formulas at the top of the tree. Okay, so now let me define a proof figure over on the third board. So a proof figure, or call it a derivation, and you might, we'll often speak of a derivation from some collection of formulas to a particular formula, but we'll define that after this, is an arrangement of formula occurrences. And I say occurrences because we want to have this, we want the option of having the same formula appear in a proof figure in different positions, and we don't want to identify them as the same occurrence of that formula. They're different occurrences. So these combine to form inference figures in the following way. So first of all, each formula is the conclusion of at most one inference figure. This is essentially, well, these sort of restrictions here are essentially forcing it to be a tree-like structure. And I say at most one inference figure because the assumptions are not the conclusion of anything. They just appear at the top of the tree. So formula occurrences which are not the conclusion of any inference are called assumptions. Assumptions can be discharged indicated by brackets and an index referencing the inference, maybe I should call it the deduction rule. Well, it's not a deduction rule, it is an inference figure. That discharged it. Now there's more to it. So every formula occurrence except one called the conclusion of the derivation is a premise of at most one inference. And a technical point is that I've used conclusion in two different ways. So there is a conclusion of an inference figure, but also a conclusion of the whole derivation. And to finish the sentence, every formula except that one is a premise of at most one inference. Just thinking about this, I should probably not say at most one. I think that's misleading. Of exactly one. And so yeah, the one exception to this rule should be the premise of no inference rule at all. And so the last condition is, I'll just say it as there are no cycles. And what I mean by that is there are no you can't write a cycle of formulas such that if you take one formula occurrence in the cycle and look at the formula which it is a premise of, then the next formula in the cycle is the conclusion of that premise. So I'm saying that there are no cycles that follow that rule for every consecutive pair of formulas in the cycle, which I hope is intuitive, that it just has this tree structure and there are no internal cycles of derivations at any point.
When you say that an inference figure is discharged, or so you mean
Oh, did I write that?
You don't mean the inference figure, do you? You mean...
I said assumptions can be discharged.
Assumptions can be discharged, indicated by brackets.
Sorry, I meant to put the inference figure that discharged it.
And they discharged it. Yeah, okay, I understand.
Mm-hmm. The last, this could be part of this definition. The last thing is to say that all inference figures must be a valid instance of a deduction rule. But one could sort of formulate this definition of a proof figure as sort of agnostic to that, and specifically because there are many different sort of collections of deduction rules that you might want to take for your particular deduction system. You might want to omit certain rules, and so then you could sort of define a valid proof figure in that particular proof system is one where all of the inference figures are instances of the deduction rules that you are considering at that point in time. So that's the sort of ugly general definition of inference figures and proof figures. Are there any questions about that for now?
I'm still not really sure so these indices, like the 1 and the 2, you really mean that those refer to the inference figure that discharges them? In which case, why have 1 and 2 on an elimination rule? I just don't know what this is. This English formulation saying what I think it says, or you mean that the indices that occur in the elimination rule in its name refer to the assumptions that are discharged, right? Not that.
So, this to use the say or elimination, or maybe let's just say to use the implication introduction rule. It's is also to decide on a particular index to use, and it's just a way of pointing out which inference rule discharged this particular assumption, because you could just discharge assumptions and then analyze the proof and recognize that it was possible to discharge these assumptions by the time you get to this point in the proof. But this is just sort of a way to point out which inference rule discharge which assumption.
Yeah.
I think if you remove the indices, then it's no longer like the lambda calculus.
Yeah, but I think this definition is not correct. I mean, you're not allowed to discharge hypotheses after they've already been discharged, for example, right? So where does that appear in this definition? I mean, I can't in the proof you wrote on the first board, I can't have the next rule be discharging hypothesis 1 again, right? So you need some rules that are managing when you're allowed to discharge hypotheses.
Right. Well, then I would just say you can only discharge undischarged assumptions.
Okay, so that's... Okay, so discharged means I read upwards in the tree from my current position to, well, you have more than one thing labeled with that index. So let's say, okay, under your current definition, unless you're careful, you can have 2 branches, one of which is discharged and one of which is not, both of which are labeled by 1.
There is no labeling without discharging.
Okay, so you're saying that I can't actually read a natural deduction proof from top to bottom, and somehow as I read it, I should be annotating it to indicate which things are discharged and which are not, in the sense that I can't actually read your first proof. If I erase the leftmost branch of the elimination rule and everything below it, that sub thing, those 2 branches...
that's not a proof.
That's not a proof because it has annotations of discharges.
That's the part that I got very confused on. So it's very, very different to the sequent calculus in that way. The sub branches aren't sub proofs.
That's gross.
Yeah, it's terrible. Right, that's my biggest complaint about this system. You don't have you have natural subgraphs that aren't subproofs. It's very confusing.
Yeah, so you could think of this as that this rule, this or elimination rule, is kind of like it takes two subproofs as arguments, but like essentially places a transparency over them with like the with the discharge with the brackets and the indices appear over those assumptions. And so to inspect the subproofs is to like see is to see the subproof without the assumptions discharged. So like you could achieve this by like traveling up from bottom to top as you pass through a rule that discharges with this index. You sort of remember, if I see that index, then like if I'm inspecting a subproof that is above the inference rule with that index, then that subproof is not that assumption is not actually discharged.
Yeah, I get it, but I think that my impression on reading the literature on natural deduction is that I am not sure there's a single reference that is sufficiently careful in setting out the rules for managing discharging and hypotheses. I think it's not complicated, but it's kind of it actually is the most subtle part of this system, it seems to me. And it's exactly the difference between natural deduction and sequent calculus. I think this is not the place for this rant, so I'll stop. But
Okay. Yeah, I think I could come up with a concrete definition that was like at least correct.
yeah, I agree.
I find these like it's better to see the natural deduction proof being constructed like temporally than to sort of see it as this static thing. Anyway, so let's get to the point of this, which is soundness. So I'll just erase this example proof. So some important definitions which weren't actually part of the semantics were, I guess you could just think of them as notation for statements about the way interpretations relate to formulas and collections of formulas. So first of all, we write, if we have an interpretation that tells you what all the symbols in a formula mean, it models a formula. That statement says that interpretation with some valuation nu of phi is equal to 1 for every valuation nu. And so this just we're just saying if a formula has free variables, the model makes it true if it's true irrespective of what those free variables stand for, which objects they stand for, because the valuation picks out the objects for the free variables. Then we write, we're just massively overloading this entail symbol here.
Sorry, I feel like there was a segue that I completely missed. Where did the free variables, where did variables come from?
So this is part of the first lecture. So these are, I guess we've sort of, the rules on the left here all look propositional just because I wrote like capital A and capital B, but these just stand in place for any formula in our first order language. So these possess quantifiers and everything. Yeah, okay, so an interpretation makes so gamma here is a set of formulas. So this just means that I is a model of psi for every formula psi in gamma. So that's just so the second definition just depends on the one before it. And then the same with this one. We say gamma entails some formula. That is true if and only if an interpretation models that formula for phi.
Sorry to go back to this first line, but when you say for every valuation the I of v of phi is 1, what does that mean? That it's equal to 1? That it's it's provable that there exists a natural deduction with that conclusion?
No. This is all back to the semantics. So an interpretation is on the semantic side. So if you have the document in front of you that was shared in the Discord, the final definition is essentially a way to, or it just defines what it means for a formula to be true in some interpretation. And we just use the sort of symbols 0 and 1 as like labels for true or false. Like you could use true or false there instead of 0 and 1, but we're just using those. We're just using 0 and 1 as the Boolean values, I guess. Yeah. So this last line is the statement being defined as gamma entails phi, and what this means is if you restrict your attention to all of the interpretations which model all of the formulas in gamma, so it makes all of the formulas in gamma true, all of those interpretations also make phi true. And with this definition, we can now state the soundness theorem. Actually, that's a lie. We need one more, which I should have done on the other board. Is with a single turnstile, gamma turnstile phi. This says that there exists a derivation whose conclusion is phi and whose undischarged assumptions are a subset of gamma, or who they form a subset of gamma. So this is the statement that phi is provable from gamma. It might not use all of the formulas in gamma, like it might not have them all as undischarged assumptions at the leaves of the tree. But yeah, that's it. Yeah. So that's our definition of provability. And so then the soundness theorem is one direction of the connection between these two relationships between gamma and phi. So the soundness theorem states that if phi is provable from gamma, then gamma entails phi. And so the content of this is, there seems to be no content here if your understanding of provable from phi is some argument about like the objects that gamma and phi are talking about. And what we strictly mean here is by use of these natural deduction proof figures, which are entirely syntactic. So they are identifications of inferences that we make based on the structure of a logical formula, like inferring A from A and B. And so the argument of soundness here is that this deduction system that works purely syntactically is actually, it essentially is saying that it doesn't make any mistakes. It doesn't. There's no way to write down a valid proof figure that uses all valid inference figures inside it and obeys all of the side conditions they have, which would prove something which doesn't actually follow from the assumptions in gamma. So that's the soundness theorem. If I had more time, I would probably go into an example of how you would prove this, but essentially you prove it by induction on the size of the proof, and you sort of break it down based on what is the last inference figure used. And then you just need to argue that for every single inference figure, all of the models that make the formula on the top line true also make the formula on the bottom line true. It's slightly more complicated than that when you have the usage of discharged assumptions. But yeah, essentially the soundness theorem is like, you can sort of view it as less of a theorem and like it's a sanity check. So like if we had a proof system that wasn't sound, we wouldn't consider that like a disproof of the soundness theorem. This would just be a criticism of the proof system that it fails to always make correct arguments. There are like some arguments that it makes that aren't reflected as valid arguments in the semantics. So we're at 12 o'clock there, so I should wrap up my...
Yeah, thanks. I think we probably have some time for questions because I don't see Adam here, and he may have had the same confusion with daylight savings time that Kenneth had. So Who knows when Adam will show up. So I think let's not rush over there. If there are questions, please proceed, and then I'll keep an eye on whether Adam shows up or not.
Well, he'll show up in 1 hour.
Oh, there's Kenneth. Yeah. Yeah. Right. So
Yeah, I made it. Sorry.
No problem. No, it's. I think I've also been in an attempt to be helpful, given times to people in their local time zone, but those are no longer correct, and I failed to think about that. So that's my fault for not just...
Daylight saving sucks.
I should just universally always talk about universal time for forever now, and never refer to local time zones. But yeah, are there questions?
I had one comment on kind of something that you were complaining about earlier, Dan. Why do you try to read... I don't know if you do, but it seems almost as though you try to read natural deduction linearly, where the whole point of that is that it's global. So I don't feel like you can read natural deduction from like the leaves down towards the root.
Well, then what is the point of it? I mean, isn't it supposed to be an artifact that reflects an argument? If to extract the argument, I have to like fart around all over the proof and figure out which overlays apply when, and then like actually it's a movie I'm supposed to watch you do when you annotate things, then like there's implicit structure. There's like a, I have to actually watch you write down this figure rather than just know to read it from one place to another place. I think natural deduction and its manager of hypotheses is simply wrong, in my opinion. I get why people did it, but I think it's wrong.
Isn't this the same though for like, I mean, just a natural language argument? Like you can't like
Well, you read that from start to finish.
I just mean that like things are so much more implicit in when I read like a mathematical argument, it sort of introduces and removes hypotheses, and you have to be paying attention to the whole time, like to sort of remember at which point in the proof which things are being assumed and
Sure,
when they are no longer assumed.
But that seems like a criticism of natural deduction. It's as hard to pass formally as an informal verbal argument. Is that what you're saying? I mean, I agree. I think the selling point of natural deduction is that it seems intuitive and easy to understand. But that's not true, because I find it hard to understand. I find it hard to understand exactly what people mean really, really by the management of hypotheses. And I think like Negri and von Plato, which is a standard text, is kind of cagey about this in some way. I mean, you can figure it out, but okay, it's not on its face clear exactly what what exactly is a natural deduction argument, right? I mean, where are labels allowed to be duplicated and not? You can spell all these things out, but by the time you've done that, I claim you've basically invented sequent calculus, and the advertisement for natural deduction as being straightforward and intuitive has gone away at some point by the time you really actually say what you mean by a natural deduction proof. Okay, I'm being deliberately provocative, but
It's a fair response. I feel like taking the perspective that I like to take, which is the mathematical objects, it's a global proof structure. So whether you think that reflects natural argument or not, that just might be an error in the intuition that you try to put onto the mathematical object in front of you, right? So that might be a way that I'm
Also,
apologetic
like,
toward.
You could like claim that it reflects a natural language argument, which is what it was invented for, without like, I mean, like maybe natural language arguments are just bad in like, but it still like models it well, I think.
Can you guys hear me? It reminds me of programming where there's like a lot of different scopes of different variables. Good programs are careful enough with this that like you can do crazy things with scopes, and that's like bad programming. But at least to me, it doesn't seem like that much of a flaw if it's kind of making use of these implicit, or you kind of have to look at the pointers to figure out which hypotheses are active when, because that does seem kind of natural. Maybe even it could be that it's natural when you're writing a proof like this and not necessarily when you're reading it. You kind of have to unpack it through time when you're reading it or something like that. I think for these kind of reasons, like it could be useful, but maybe not just as like a 2D rendering of a proof, because it has a bit of complexity hidden in like a third dimension.
Yeah, I agree with that.
The reason why you see the analogy to scopes and programming is because the natural deduction is the same system as the lambda calculus.
Some subset of what you presented is anyway.
Yeah. So, if you take out like the classical inference rules, which are over here, well, only the first one, the proof by contradiction one, and the quantified rules, and I guess the quality ones, then you're left with intuitionistic logic, which is the same as the simply typed lambda calculus. And it also obeys a normalization theorem, the same as the lambda calculus, obviously.
Do you think there's a link to imperative programming languages? Because I think there's a couple of steps between that and something that's so purely functional as lambda calculus or a functional programming language. I think that when I'm programming in Python or something like that, that has these scopes, or C or whatever, I'm kind of visualizing the code is like a 2D rendering of a syntax tree. But there is always a third dimension of when this is running, it's happening in a sequence through time, and kind of information is flowing from some variables to other variables. And a programmer is kind of able to keep that in their head as they're programming in order to craft the bit of code that they're working on. That maybe that's a little bit similar. Like that activity that you do with your brain when you're programming could be a little bit similar to kind of what you have to do to read a natural deduction proof, I guess.
I would like quite firmly believe in that. Yeah, I see that similarity quite strongly.
This actually raises like another question that I've had for a while, and I think this is like a noob question. When you talk about, when I think about, when you were explaining this kind of thing, when you read out the natural language argument, I can't help but think that like was it or elimination or whichever one is kind of like a switch case or an if else in a program, like an imperative program. So I wonder if there's, and I've always thought of quantifiers, like for all, like the universal quantifier, as just like a for loop in a program. Do you think there's a way of, I know that programs and proofs are related, but do you think there's a way of realizing it at this level, like where the mapping is from universal quantifiers to for loops, and from these cases, these disjunctions, to like if then else?
I don't think the connection between for loops and quantifiers is correct, but
yeah,
I mean the system with quantifiers is related to system F, which is what's underneath Haskell, for instance. So, yeah.
But that's what I'm not interested in, because that doesn't have for loops. Like it's not imperative.
Yeah.
Yeah. So and something preventing for loops being like universal quantification is that like to introduce a universal quantification. We didn't talk about any of these rules, but yeah, you prove that some formula about some formal symbol A holds true without assuming anything about A.
Yeah.
And then you're allowed to introduce universal quantification over that thing. A false instance, a false version of this rule would be to have a rule where like it has infinitely many premises that are like you take all of the terms of the language and prove it somehow systematically for all of those. That's like both too big of an inference rule and too small. It's too big because it's obviously unreasonable and like makes the proof system not a finite thing you can write down. But it's too small because you can have interpretations where not every object is named, and interpretations where you can't hope to name every object.
Yeah. Okay.
So I mean, I guess like for loops are like you do sort of abstract the variable that you're like performing the for loop over, but like they have to be finite, or like they can't be anything uncountable about like what you're performing the for loop over.
Yeah. Okay. Yeah, I buy that. At least without some more thought, I think that's a bit of a dead end for me at the moment.
As you were talking about before about like the or elimination rule is like the like writing a switch statement or something. That's like in say Haskell, when you like we have algebraic data types.
Yeah.
Where you can define something as like something of this type is either this or this. Yeah, that's the sort of the disjoint union operation on types, and so like the disjunction can be thought of as disjoint union of types, or the co-products, I guess, and in conjunction with the product as well.
So I have a kind of newbie question. So why prefer this kind of system of asserting which formulas are true or false as opposed to like truth tables or something like that? I mean, that's often how undergraduates are taught how logic works, right? If you have a formula, it's true if the truth tables say it's true.
Yeah, well, then so the first answer is that that's just restricted to propositional logic. But even in the propositional logic case, you're you have it's completely unwieldy because you have way too many rows to verify, even with a modest number of propositional variables involved. And you might sort of recognize some variables to be irrelevant, or like you might start reasoning about the truth table on the basis of the connectives involved. But when you reason about the truth table, all of that reasoning can be boiled down to syntactic rules, and the deduction system is just a formalization of that. There are other deduction systems like Tableau, which essentially you start with like the premises and the negation of the conclusion, and you sort of apply particular operations to the formulas based on what their main connective is, and you try and reach a contradiction at every branch that shows up. So there are many kinds of deduction systems. I would just like in a very broad sense, they all account for reasoning about the truth table. So the soundness theorem is that it like gets things correct, and the completeness theorem will be that it like is able to make all of the deductions that could be made.
You said that the truth table gets kind of unwieldy, but for certain questions, it seems like you can't do much better from a computational complexity point of view. Something like in the worst case, if you want to know that your formula is satisfiable, that's the SAT problem. So you can't do better than enumerating the truth table you can't do better than enumerating the truth table as far as we know.
Yeah, so there's a distinction between taking some formula, not knowing whether it's like a contradiction or a tautology, and trying to discover what the right fact about it is. And then there's, all right, if you reckon it's one or the other, like how difficult is it to verify that and to sort of present that verification?
Okay.
And it's the presentation of the verification that's the strength of the like formal proof system.
Yeah. Okay. So if you have like this is easy in one way and hard in the other way, because if you have the right row of the truth table, you can show that it's satisfiable. But if it's one where the formula is true, because you only need one of those. In a similar way, maybe it's like in some cases, if you have the right proof, it's easy. Is it just like in some cases this is a clever way, but in some cases it's just as hard as
there's the two goals. There's showing satisfiability or non-validity is about like one row of a truth table. So obviously truth tables are better if you're just verifying. But then showing something as a contradiction or a tautology is the other extreme, at which if you're using a truth table, you're forced to reason about all of the rows. But with a proof system, you can you can essentially show where the problem is, so that like here, because I can show A and not A, it doesn't matter like what the other variables.
Okay.
How the
Okay.
other variables.
It's like a
are.
shortcut for talking about the whole truth table.
Yeah.
Okay. That sounds good.
Yeah, and these deduction rules are only valid deduction rules if they sort of make correct inferences. Like the inferences they're making might only involve certain variables, but the validity.
Oops.
Yeah, what happened? My like Discord just restarted. What was I saying? I kind of. The inference rules might involve only some of the variables, but they should nevertheless like make claims that are true for like truth valuations of all the variables.
Yeah.
I guess I like another perspective on this. I mean, I don't know if this will, if anyone here will like this, because I sort of sense a disdain for philosophy. But these proof rules were these deduction rules were presented to me, or like my first interpretation of them were sort of on like if you can look at these deduction rules and like ignore that it's written like the and rules are written with an and symbol, and on the basis of like just on the like if you're hoping that if what you know is that these deduction rules here are sound, you can essentially discover the truth table for conjunction and then sort of realize that it is conjunction. And so I think for some logicians would claim that that these deduction rules themselves for conjunction actually explain what conjunction is, like at least better than some truth table that tells you under which conditions, like that just enumerates the 4 different cases when A is true, B is false, like it's false.
Absolutely. I mean, it's a crime to teach people what implication means by talking about the truth table of the implication symbol. It's ridiculous.
Yeah, everyone always gets tripped up by that. And yeah, so I think you can actually sort of, you can look at these rules. If you look at the first rule and you want this, like you don't know what the semantics of and is, and you want this to be a sound deduction rule. Well, I need it to be the case that if A is true and B is true, then A and B is also true. So that tells you just the 4th row of the truth table, the one where A and B are true. Then the second, like maybe I should actually just write this in the bottom right corner of this board. A and B 0 0 1 1 0 1 0 1. So A, B gives you A and B. If that's sound, that tells you that the 4th row is 1. It doesn't tell you anything about the other 3 rows. So you could have a deduction system which has this deduction rule, and maybe the symbol, the connective here is kind of a mystery. You can discover that the 4th row of this truth table has to be true in that case. And then the other rules fill in the other cases. So the first conjunction elimination rule tells you that, well, if A and B is true, then A has to be true. But also if A is, like the converse of that is that if A is false, then A and B also has to be false. So that tells you that these 2 rows are false. And then the other rule, A and B gives you B, tells you that these 2 rows have to be false. And I believe you can sort of go through the same process with the other rules. So you could sort of convince someone of these rules as just this is what it means to claim A and B, is to present A and to present B. And what you can get out of A and B is you can get A out and you can also get B out. And that's sort of these pairs of introduction and elimination rules essentially characterize what the semantics has to be.
More than that, I would say that's exactly the exercise that Boole did in his book to invent that thing that you have put on the board there. I mean, of course, the notion of deduction and the meaning of or and is prior to the idea of assigning 0 and 1 to propositions in some way and combining them arithmetically to determine the truth of other propositions. So it's kind of an artifact of the way we teach logic, that we kind of maybe teach this truth table business first, and then this other thing comes afterwards.
Yeah, and like when we have these sort of truth table things, it like teaching someone intuitionistic logic that is completely internalized this idea is like the idea of truth values and the sort of truth functional semantics with truth tables is like impossible. But it makes a lot more sense to start with some sort of deduction rules about like in conversation what it means to what are the conditions under which I can introduce an assertion of A and B into the context? Is it when I have A or when I have B, or the same with the or rules or the other rules?